Hi everyone. Nice to meet you. I am Her, Technical Manager of MIDAS IT. In this webinar, we will introduce the newly added functions through the Gen 2022 release. I would like to introduce the new ACI code, ACI318-19, which is one of the most standout among the new features. The table of contents is as follows. This webinar is divided into two sessions. Session 1 is the time to learn about the newly revised ACI318-19 code. In this session, we will look at the changes from the previous code, ACI318-14. In Session 2, it will be a time to design a sample structure based on ACI318-19 in the Gen 2022 program, released this month. Let's start Session 1. Among the changes from the existing standard, ACI318-14, you can see the notable changes in ACI318-19. Aren't you curious about what's changed with the new ACI code? Let's get started now. ACI318-19 has several notable changes. The major changes are as shown. 1. New rebar material and revised limitations. New provisions are introduced for the use of high-strength reinforcing. ACI318-19 permits the use of grade 690 reinforcement to resist moments and axial forces from gravity and wind load combinations. The use of higher-grade reinforcement raised concerns about serviceability like cracking and deflections, which were addressed through a series of changes for slab and beam minimum reinforcement, effective moment of inertia, and requirements for deflection calculations for two-way slabs. Therefore, the limitations also revised due to the use of high-strength reinforcing bars. 2. Minimum reinforcement provisions are revised. The minimum flexural reinforcement regulations according to the reinforcement type and grade were integrated into one. 3. New reinforcement strain limit is introduced for non-prestressed members. This is new definition of epsilon T associated with tension-controlled limit. 4. Significant updates to one-way shear and two-way shear calculations. Maybe this section is large change parts from ACI318-14. ACI318-19 sections on one-way shear and two-way shear, i.e. punching shear, consolidate what were previously a wide range of equations. 5. Hanger reinforcement provisions are introduced. 6. New equation for effective moment of inertia for cracked section. It has been changed to an equation similar to the Eurocode. 7. Modification of development length provisions. New variables and factors emerge. 8. Lastly, modification of earthquake-resistant structure provision. The details will be explained next. A major thrust of the ACI318-19 code cycle was to expand permissible applications of high-strength reinforcement. Current U.S. building codes limit rebar strength based on decades-old research, with most reinforcement used in concrete construction in the United States being grade 60. Producers are now able to produce these rebars, however, that is almost twice as strong as it was several decades ago. Strength and ductility concerns were addressed by introducing new requirements for mechanical properties of reinforcing bars, adjusting the method for calculating the strength reduction factor for moment and combined moment and axial load, revising development length provisions, and limiting the value of Fy that can be used for calculating the maximum axial compressive strength (PN) max of columns. It is likely that grade 690 reinforcement will be used mostly for vertical bars of shear walls and columns, though it might also be used for heavily loaded floor systems. Substantial new research and others has demonstrated acceptable performance of members of special seismic systems reinforced with grade 550 reinforcement and grade 690 reinforcement. Recognizing this, ACI318-19 now permits special moment frames with grade 550 reinforcement and special structural walls with grade 550 and grade 690 reinforcement. The provisions allow the use of the higher grades to resist moments, axial forces, and shear. To accommodate these higher grades, additional restrictions on hoop spacing, beam column joint dimensions, and lap splice locations have been added that will contribute to more reliable performance of special structural systems. As mentioned earlier, in the ACI318-19 standard, high-strength rebar supplemented with elongation is used and improved to allow high-strength rebar special seismic systems. For usage of flexural, axial force and shrinkage and temperature, also shear forces, Fy, 550 MPa grade, is allowed for special moment frames. Also, 690 MPa grade is allowable to special structural walls. But, longitudinal reinforcement over 550 MPa is not permitted for intermediate moment frames and ordinary moment frames resisting earthquake demands. ACI 318-19, Table 8.3.1.1 for minimum thickness of non-prestressed two-way slabs without interior beams is revised to include grade 550 reinforcement. This change affects the calculation of minimum slab thickness for Fy exceeding grade 420. The previous code that allowed up to grade 520 was changed to grade 550, and related regulations were modified. For the calculation of the minimum flexural reinforcement amount for beams with Fy exceeding 550 MPa, ACI 318-19, 9.6.1.2 states that the value of Fy shall be limited to a maximum of 550 MPa. ACI 318-14 did not permit the use of flexural reinforcement exceeding 550 MPa for beams. This change affects the flexural designs of beams with Fy exceeding 550 MPa. The S-min values calculated by equations 9.6.1.2a and b will be same as for grade 550 reinforcement, even if the higher strength reinforcement is utilized in the design. For the calculation of the maximum axial compressive strength, Pn max, for non-prestressed and prestressed members with exceeding grade 550, ACI 318-19 states that the value of Fy shall be limited to a maximum of 550 MPa. ACI 318-14 did not permit the use of reinforcement exceeding grade 550. This change affects the designs of structural members with exceeding grade 550. The P0 values calculated by equations and will be same as for grade 550 reinforcement, even if the higher strength reinforcement is utilized in the design. ACI 318-19 states that along development and lap splice lengths of longitudinal bars with exceeding grade 550, KTR shall not be smaller than dB. ACI 318-14 did not permit the use of flexural reinforcement exceeding grade 550 for beams and columns. The requirement for a minimum value of KTR along development and splice lengths improves ductility. ACI 318-19, 8.3.1.1 states that for Fy exceeding 550 MPa, the calculated deflection limits in 8.3.2 shall be satisfied assuming a reduced modulus of rupture, Fr equals 0.41 squart, Fc for two-way slab. This change leads to higher deflections for exceeding grade 550 in a non-prestressed two-way slab systems. Secondly, minimum reinforcement provisions are revised. ACI 318-14 requirements were based on reinforcement type and grade. ACI 318-19, 7.6.1.1 states that a minimum area of flexural reinforcement, AS-min, of 0.0018 Ag shall be provided. If deformed bars with the yield strength of reinforcement is less than grade 420, the minimum area of flexural reinforcement, AS-min, was equal to 0.0020 Ag. Therefore, the AS-min requirement is reduced by 10% in ACI 318-19. If deformed bars with the yield strength of reinforcement is more than grade 420, the minimum area of flexural reinforcement, AS-min, was greater of two equations. Therefore, the AS-min requirement stayed unchanged for grade 420 reinforcement in ACI 318-19. However, for higher grade reinforcement, there is an increase in the AS-min requirement. For example, for grade 550, grade 690 reinforcements, the new S-min requirement is 0.0018 Ag, instead of the ACI 318-14 value of 0.0014, 28.6% increase in ACI 318-19. This change unifies the minimum flexural reinforcement requirement, irrespective of reinforcement grade. In ACI 318-19, minimum shear reinforcement in non-prestressed beams are also revised. In ACI 318-14, the formula using the VC calculation formula was judged, but in ACI 318-19 it has been changed to a fixed formula. But it seems almost no numerical impact between 14 to 19 as shown. Third, new reinforcement strain limit is introduced for non-pre-stressed members. Before ACI 318-14, the compression-controlled strain limit was defined as 0.002 for grade 420 reinforcement and all pre-stressed reinforcement. But it was not explicitly defined for other types of reinforcement. The compression-controlled strain limit eddy is defined in and for deformed and pre-stressed reinforcement respectively. Beams and slabs are usually tension-controlled, whereas columns may be compression-controlled. Some members, such as those with small axial forces and large bending moments, experience net tensile strain in the extreme tension reinforcement between the limits of epsilon Ty and epsilon Ty plus 0.003. These sections are in a transition region between compression-controlled and tension-controlled. In ACI 318-19, table for strength reduction factor phi. For moment, axial force, or combined moment and axial force. The tension-controlled strain limit is defined as an expression of Fy to explicitly cover non-pre-stressed reinforcement grades other than grade 420. Therefore, beginning with the 2019 code, the expression epsilon Ty plus 0.003 defines the lower limit on OT for tension-controlled behavior. ACI 318-14, 7.3.3.1, 8.3.3.1 and 9.6.3.1 stated that for non-pre-stressed slabs and beams, epsilon T shall be at least 0.004. ACI 318-19 states that non-pre-stressed slabs and beams shall be tension-controlled in accordance with table. This change leads to more economical designs for non-pre-stressed slabs and beams by eliminating the need to add more tension steel just to satisfy a lower steel strain limit, without any gain in the flexural design strength, due to reduced strength reduction factor. Number 4. Significant updates to one-way shear and two-way shear calculations. One-way shear strength provisions in relation with VC, for non-pre-stressed members, are modified substantially. ACI 318-19 updates shear capacity to reflect research findings on the effect of flexural reinforcement, ρ, W, and section depth, size effect factor, lambda s, using test data. Chapter 22551 states that shear forces of concrete for non-pre-stressed members shall be calculated by Table 22551 and 22551 through 22551-3. The new Table 22551 is titled VC for non-pre-stressed members and aims to unify the ACI 318-14 provisions of for non-pre-stressed members without axial force in 2255. For non-pre-stressed members with axial compression in 2256. For non-pre-stressed members with significant axial tension in 2257. The new Table 22551 introduces a criteria for AV and AV-min that results in set of equations to calculate VC. 22551-1 states that VC shall not be taken greater than 0.42 lambda squared FC BW D. 22551-2 states that in Table 22551 that value of shall not be taken greater than 0.05 FC. 22551-3 states that the size effect modification factor lambda s shall be determined by equation 22551-3. The changes account for size effect and low reinforcement levels for members without shear reinforcement. It also simplifies and reduces the equations for non-pre-stressed concrete members with and without axial load effects. The impact of this change will vary and can only be determined after implementation for various conditions. Size effect factor, lambda s, is the factor used to modify shear strength based on the effects of member depth. As you shown left graph, it become less than 1.0 and d, effective depth is 250 mm as the starting point. Rho, W included in Table 22551 VC for non-pre-stressed members, the longitudinal flexural reinforcement affects the shear design. As the longitudinal flexural reinforcement ratio increases, the shear capacity of concrete increases. Compared with the constant 0.16 lambda in ACI 318-14, if the longitudinal reinforcement ratio is about 1.42% or more, the shear capacity by the formula of ACI 318-19 is greater than that of ACI 318-14. As you can see, ACI 318-19 table now incorporates the size effect factor, lambda s, in equations A, B, and C. Likewise, this change accounts for depth effect of slabs without shear reinforcement. For two-way slabs without shear reinforcement, and if effective depth is more than 250 mm, the size effect factor will result in reduced two-way shear strength values as compared to ACI 318-14. The interaction of one-way shear forces acting along orthogonal axis shall need to be considered per ACI 318-19, as provision 22.5.111 states that if shear ratio is more than 0.5 by each directions, equation 22.5.111 shall be satisfied. Chapter 11.542 states that Vn at any horizontal section shall not exceed 0.66 scored FC, ACV. In ACI 318-14, the limit for in-plane shear, the nominal shear strength, Vn, was 0.83 scored FC. This limit is intended to guard against diagonal compression failure in structural walls. The change creates consistency in the calculation of the in-plane shear strength of structural walls between Code Chapters 18 and 11. However, it has no numerical impact as the D is already taken as 0.8 LWN, a CV equals to H LW. ACI 318-19, 11.543 states that to improve consistency in the code, the nominal in-plane shear strength equation in section 11.543 now has the same form as the shear strength equation used in section 18.10.4.1. Accordingly, the sections 11.546 and 11.547 of ACI 318-14.4.5c calculations and section 11.548 of ACI 318-14 for 5s calculation are completely removed from ACI 318-19. The detailed calculation option allowed within wall is also removed by the removal of the ACI 318-14, table 11.546. The impact of this change can only be determined after implementation for various conditions. This change results in a similar threshold value for factored shear force at section criteria where minimum reinforcement shall be acceptable. In ACI 318-19, depending on the height HW by the length LW of the entire wall, the limits values may change. Number 5. Hanger reinforcement provisions are introduced. Table 9.7.6.2.2 introduces new maximum spacing of legs of shear reinforcement criteria across the width of beams. Also, a new figure is added to the commentary titled Figure 9.7.6.2.1. Hanger reinforcement for shear transfer. This change improves shear behavior of wide beams that require stirrups by providing multiple stirrup legs. This new criterion affects the determination of the number of legs across the width of a wide beams in design. Number 6. New equation for effective moment of inertia for crack section. 24.235 states that for non-prestressed members, unless obtained by a more comprehensive analysis, effective moment of inertia shall be calculated in accordance with Table 24.235. As stated in 24.235, the effective moment of inertia approximation developed by Bischoff and Scanlon is adopted in Branson equation, as per ACI 318-14 24.235a, is removed from ACI 318-19. It has been changed to an equation similar to the Eurocode. The commentary further states that the ACI 318-14 equation 24.235a has been shown to underestimate deflections for members with low reinforcement ratios, which often occur in slabs, and did not consider the effects of restraint. For members with greater than 1% reinforcement and a service moment, at least twice the cracking moment, There is little difference between deflections calculated using the ACI 318-14 provisions and the ACI 318-19 provisions. Number 7. Modification of development length provisions. In 25.4, the development length equations are revised to cover high-strength reinforcement and concrete to account for spacing between bars. New modification factors, such as psi g to modify development length based on grade of reinforcement, are introduced. In ACI 318-19, it is also considered reinforcement grade factor, psi g, for general method for calculating development length in tension, LD. For calculating development length of standard hooks in tension, concrete strength factor, psi c, is considered according to concrete compressive strength, FC. And psi o, location factor, and psi r, confining reinforcement factor, is redefined in ACI 318-19. Number 8. Modification of earthquake-resistant structure provision. In ACI 318-14, the amount ratio of longitudinal reinforcement in beams of special moment frames, ρL, shall not exceed 0.025, regardless of the rebar strength. However, in ACI 318-19, in case of grade 550, ρL shall not exceed 0.02, not 0.025. In ACI 318-14, hoop spacing S0 over a length L0 in columns of intermediate moment frames shall not exceed the smallest of 4 cases. In ACI 318-19, according to the rebar grade, the limitation is different, and smaller spacing should be satisfied than ACI 318-14. Hoop spacing in beams of special moment frames shall not exceed the smallest of 3 cases in ACI 318-14. However, in ACI 318-19, the limitation is different, 5 times of diameters, not 6 times of the smallest primary flexural reinforcing bar for grade 550. In ACI 318-14, spacing of transverse reinforcement of special moment frames shall not exceed the smallest A through C. In ACI 318-19, for grade 550, the limitation is different, 5 times of diameter, not 6 times of the smallest longitudinal bar. Design shear forces in special structural walls in ACI 318-14 shall be obtained from the lateral load analysis in accordance with the factored load combinations. In ACI 318-19, the design shear force shall be calculated by equation eq 1031 as A by additionally multiplying omega v over strength factor and omega v factor to account for dynamic shear amplification. Design shears for structural walls are obtained from lateral load analysis with appropriate load factors increased to account for flexural overstrength at critical sections where yielding of longitudinal reinforcement is expected, and dynamic amplification due to higher mode effects, as illustrated as figure above. Because Mn and Pr depend on axial force, which varies for different load combinations, and loading direction for flanged and coupled walls, the condition producing the largest value of omega v should be used. Although the value of 1.5 in 18-10-312 is greater than the minimum value obtained for the governing load combination with a phi factor of 0.9, and a tensile stress of at least 1.25 Fy in the longitudinal reinforcement, a value greater than 1.5 may be appropriate, if provided longitudinal reinforcement exceeds that required. Dynamic amplification is not significant in walls with HWLW less than 2. A limit of 0.007 HWCS is imposed on NS to account for buildings with large story heights. The application of omega v to 5U does not preclude the application of a redundancy factor, if required by the General Building Code. If you learned about the notable changes of ACI 318-19 in Session 1. In Session 2, we will have time to demo the design through ACI 318-19 in new version. The sample model we are going to check is a 12 stories RC structure. The floor plan of the building, as you can see, has a rectangular shape with a width of 36 meters and a length of 27 meters. In addition, the total height of the building is 50 meters. And the height of a typical floor is 4.0 meters. It is a building for office use, and the second and third floors are for store use. As customary standard was used for materials, and grade 550 and grade 420 for deformed bars were used. In the case of concrete materials, for vertical members, the first to fourth floors, which are the lower floors, are used grade C32, and the upper floors grade C28. In the case of gravity load, it was referred to the reference standard ACI 7. Lateral load also referred to the ACI 7 code. For seismic force resisting system, it is used dual system. Special reinforced concrete structural walls with intermediated moment frames as per table 22 of ACI 7 code. And for wind loads, it is used this conditions. Basic wind speed is 85 mph and exposure category is B. This is the load map for gravity loads per floors. We can set lateral load like these. Generate design spectrum for seismic load. And wind load set at the right side. So, let's get started demo with Gen 2022. So, now let's get into the demonstration. Let's run MIDAS General program. In new version, General 2022 1.1, you can easily open files you have recently worked on. Click the model. Then, the file has been opened. As you look at the work tree menu, as mentioned earlier, material data, section data and wall data are entered. In the case of the floor load, I put it in each floor using the assign floor load function. We will also check wind load data and seismic load data. And let's check the load combinations. When we open the Modify Concrete Materials dialog box, you can see that the material information has been entered as follows. Because we want to review based on the SI unit, as customary SI concrete and rebar data has been entered. For vertical members like columns and walls, C32 was used for the lower stories, and C28 was used for the upper stories and girders. The grade of main rebar is used as grade 550 MPa of design yield strength, and sub-rebar, grade 420. Longitudinal reinforcement over 515 polyma is not permitted for intermediate moment frames. So for the main rebar, we used grade 550, which is the maximum that can be used. In the case of special structural walls, up to grade 690 is allowed, but it is designed as grade 550 to match the type of rebar to the column. Let's check if the concrete design code is entered as desired. Apply special provisions for seismic load is checked. As the frame type, immediate moment frame is selected, and special RC structural wall is selected. For the boundary element method, a displacement-based method is selected. As suggested in the criteria, enter the amplification factor as 5.0 and the importance factor as 1.0. Please check the other settings below as well. Okay. Then let's proceed with the member design. Let's do the beam design at first. The default shortcut is to press Ctrl and the number 1 together. Depending on the number of elements and nodes entered into the modeling, the design speed may vary. Beam design results are complete. Looking at the govern load case as expected, second load combination, which is one of gravity load combination cases, has the most, and also seen seismic load combination cases like 23rd or 24th. If you move the button from Sort by Properties to Sort by Members, you can check the design results for single member results. If you check the Connect Model view and select the corresponding members, you can immediately check the location of the element you want to check in the model, as you can see. I'll select one member for example. Then, click the graphic button shown below. Then the graphic result window appears. The graphic result window is composed of graphics and tables so that the user can intuitively check the design result of the member. For beam design, they are listed in order of design information, bending moment capacity and shear capacity. You can check this result and check the demand and capacity of the member. It can also help you build a structural list of beams. Close the graphic result window, and now we want to check a more detailed design result report. If so, please click the Detail button. This button can call the Detail Result Report. Before that, the part you need to check is to check the detail print position. In the program, the review is divided into 3 positions of the members, end I, middle, and end J. After checking the Check button, click the Detail button. You can see that Ms. Word is created. You can quickly find the review by clicking on the title section on the left. You can check from the nominal moment capacity to calculate the design shear force to satisfy the strong shear clause required by the code. It is then listed in the order of bending moment check and shear capacity check. If you want a detailed design process, you can check the Detailed Design Report. The chapter number of the ACI code applied to the review is also written on the right side of the content. Therefore, it is configured so that you can check the contents while searching for the corresponding code. Next, we proceed with the column design. The default shortcut is to press Ctrl and the number 2 together. Column design results are complete. Looking at the govern load case, second load combination, which is one of gravity load combination cases, and also seen seismic load combination cases like 27th or 28th. In the result dialog, you can see the design result of column members. When show the graphic result, they are listed in order of design information, axial and moment capacity, including PM interaction curve and shear capacity, end part and middle part, and Y direction and Z direction of the column. Move the button from Sort by Properties to Sort by Members. We check the design results for each member results. If we select the sample members and press the Detail button, we can see that Ms. Word is created. We can check from the member information after design, axial capacity and moment capacity, and then shear capacity. If you want a detailed design process, you can check the Detailed Design Report. The chapter number of the ACI code applied to the review is also written on the right side of the content. So, it is configured so that you can check the contents while searching for the corresponding code too. Lastly, we proceed with the RC wall design. The default shortcut is to press Ctrl and the number 3 together. Wall design results are complete. When show the graphic result, they are listed in order of design information, axial and moment capacity, including PM interaction curve by Y direction and Z direction, and shear capacity of in-plane directions. Move the button from Sort by Wall ID to Sort by Wall ID including stories. We check the detail results for each wall member more detail. You can check from the member information after design, axial capacity and moment capacity, and then shear capacity. Now let's try another test. I have already prepared the same model, but this model is set based on ACI 318-19 unlike our model. The reason for this test is to check the difference between the design results of the existing standards 318-14 and 318-19. To do this, first, automatically design all 14 standards of modeling, and then by pressing the Update Rebar button, rebar information is entered. Now in this modeling, after changing the concrete design standard to ACI 318-19, we will do concrete checking with rebar information already entered, not concrete design. First, let's check the beam design as the same amount of rebars as in the 14 standard in the 19 standard. If we sort only the parts that are in, the demand capacity ratio of shear is not satisfied in some beam members. Shearing is generated from about 1% to as much as 20% as you shown. As mentioned earlier, this is because the effect of significant updates to shear. We explained that the change in shear capacity calculation is also related to the amount of flexural reinforcement, rho, W. Also related to size effect factor, lambda, S. This is obviously not the case in all cases, but in this case, we can determine that the 19 standard requires a greater amount of shear reinforcement or flexural reinforcement than before, ACI 318-14. Let's check the columns as well. In the case of columns, the design of all members is good. Why is everything okay in this case? The reason is probably because, even in the design of the 14 standard, the governed ratio of the shear reinforcement is determined by the rebar spacing clause, where the size of the column acts as a variable, not the 5S requirement by the member force, 5U generated. Finally, let's check the wall. The results of walls that were all okay in the ACI 14 standard, on the contrary, in the ACI 19 standard, some walls show NG in the shear capacity check. As in the case of beam design, this is because the provisions for shear design have been changed, and it requires a greater amount of vertical and horizontal reinforcing bars for wall design. We confirmed the design result as per 19 standard, with the amount of same rebars designed as per 14 standard. We can find that the difference was quite between ACI 318-14 and ACI 318-19. So far, we've looked at the ACI 318-19 design on the Gen 2022. This concludes our webinar. Thank you for listening. I was happy to introduce you to an overview of the new ACI design codes, ACI 318-19. If you have any additional questions, please feel free to ask. And if any further questions after the webinar, please contact us. We look forward to seeing you at our next webinar.